All right, the very first question here says define the radian. A radian is just a way to measure angles. You may recall at the beginning of this school year, we looked at an equation that said r, the physical size of some object, is equal to the distance times the angle theta. But theta had to be in radians in order for us to use this equation. And that's because the way that the radian is defined. So you have a circle, and if I were to go from my bad, everybody. That's what I was putting up there. If we were to go from sort of an edge of the circle to the center, that's the radius. Now, what if we started climbing up the edge of this circle? If we cover a distance along the arc of the circle that's also equal to the radius, then we've just swept out 1 radian of angle measure. Okay. Let me clear that. So a radian is the angle that is subtended when the arc of a circle is equal to the radius, right? So it's kind of like we've got a circle, we've got a radius r, and if we start going up the circle this way, eventually we'll have covered as much distance as the radius, and that angle right there is 1 radian. If you go all the way halfway around a circle, you'll find that there's a little bit more than 3 radians of angle there. There's actually 3.14159 radians. There's pi radians in half a circle. So some useful information that doesn't really define the radian, but it's still helpful to know. There are 2 pi radians per 360 degrees. All the way around a circle, there's like 6.28, right? 2 times pi is about 6, a little bit more than 6 radians. So a radian is a pretty big angle. There are pi radians in 180 degrees. So again, a radian is a ratio between the arc length sort of around a circle and the radius, right? So it's like a ratio of those 2 things. Again, a sort of a textbook definition. So a radian is the angle subtended by the arc of a circle equal to its radius. You can maybe look that up in like a math dictionary. Now let's put that math to good use down here. It says we've got a telescope and it gives a clear view of a distant object when the angular displacement between the edges of the object is at least this many radians. The moon is approximately this far away from Earth. Hey, that's kind of what we're focused on our scale models, right? How far away is the moon from the Earth? We want to estimate the minimum diameter of a circular crater on the moon's surface that can be seen using the telescope. And so this is going to be if we're sort of looking out from Earth, there's a certain angle measurement that's the limit of our telescope, and there's a crater on the moon that we're trying to sort of observe there. So we know that the moon is a distance of 3.8 by 10 to the 5 kilometers away. We know that the angle that sort of is our maximum sensitivity is this, and we're just using the equation r equals d theta to solve for r, the physical size of this crater. And so it's just the distance, 3.8 by 10 to the 5 kilometers. Note that our answer is in kilometers, so we don't need to convert those units, times the angle. So the angle is dimensionless. The radian, again, is a ratio. So 9.7 by 10 to the negative 6 times 3.8 by 10 to the positive 5. And we find that you'd be able to see craters that are 3.7 kilometers big. But that's the minimum diameter. You could see obviously things bigger than that. If there's a big crater, you know, you'd be able to see it bigger than that, but that's sort of the smallest that we'd be able to see because that's our angular resolution of our telescope. The question goes on to ask, suggest why craters of the same diameter as that calculated in 1, but on the surface of Mars are not visible using this telescope. And so if we can see something on the moon that's that small, we wouldn't be able to see it on Mars because Mars is so much further away, right? That's sort of the limit at that distance. And so the sort of short answer to this question is Mars is further away.
We have a bus change. Bus M25 students will be riding